Hello. Wow, this is a really big room, and this is like the last session of the day. So thank you for coming and filling out the seats and making me feel a little bit better about this talk. We got a minute left, and there's still some people coming in, so I'm just going to slowly roll into this talk. First of all, thank you for coming to Oculus Connect. I hope it was a useful 2 days for you. After this, you can go have dinner and drink and meet your fellow developers, and yeah, it'll be great. What I want to talk about today is performance, particularly performance on mobile devices, Gear VR and now Oculus Go. And specifically what I want to talk about is performance on building in Unity. And even more specifically than that, I want to talk about draw calls. The alternative name for this talk that did not fly, although I liked it quite a bit, was Who You Gonna Draw Call? I thought Too Close to Draw Call was pretty good. But my name is Chris Pruett. I'm the head of development engineering at Oculus, and basically that means my job is I'm an engineer that works with folks like yourselves to make the content that ships on our platforms as good as possible. And a large part of my job is helping folks make their Unity scenes faster by reducing the total number of draw calls. So today, I'm going to talk about a bunch of the different methods that I use. Can I just get a show of hands? How many people have shipped like something for Gear VR? All right, awesome, and in Unity. And you had problems with draw calls. All right, hang on a second. So for those of you who've done this before, some of this talk is going to be a little bit maybe review. I'm going to start at the top. I'm going to explain the stuff that's sort of the basics of draw calls and what batching means and what that is in Unity. But then the last half of the talk, I'd like to get into some, less normal or perhaps unorthodox ways to further improve our frame time by optimizing draw calls. And I'm going to do it all using this scene, which you cannot see. Oh, closer. Not quite. There it is. All right. So this is a scene that I worked on last year. It's built in Unity. It's this sort of, whoa, wrong button. Don't click that button. There it is. OK. They should definitely not give me a button that turns off the display. This is a scene that, it was built for mobile VR. It was, the design of the scene was to be a efficient mobile scene. And it's not very complicated. It's just a sort of underground bar, kind of a dive bar. And we can kind of zoom in on it. I think we can zoom in on it. There we go. And it looks pretty nice, and it should run pretty well. All of the lighting is static. The geometry is not particularly complicated. It's been made to look really nice by a good artist, but the scene complexity is well within what we would expect to run on like Gear VR. However, if we ran this today on Gear VR, what we'd see is that our frame rate is really crappy. In fact, it's about 35 frames a second. And in fact, the way that I took this image, this is actually a screenshot from a Gear VR device that's running with a tool that we just released on Monday, which is called Ovr Metrics Tool. And it can, if you download it and install it on your phone, it can draw like a real-time performance graph like this on top of your VR software. It also gives you a 2D report at the end of your session. It's pretty cool. So while this scene should be fast, it's not very fast. And what I'm going to do in this talk is try to get this scene to 60 frames a second. Furthermore, I'm going to do this without actually using any complicated profilers. We're not even going to use the Unity profiler for this. All I'm going to do is assume that the slowest piece of my render pipe is draw calls, and I'm going to try to optimize those. So we'll check back in with the actual performance from time to time. My first stop to improve draw calls is just to pull up the statistics window, which is kind of this thing that floats in the top right-hand corner of the editor. And if we zoom in on it, we can see that we got like a crap ton of draw calls. So 960, Unity calls them batches. I think that's a sort of confusing name to use, but they're the same thing. 969 draw calls for this scene is sort of way out of bounds. In fact, we would like this to be more like 50 maybe. When we look at a scene this way in the editor, we're actually only seeing what it costs to render a single eye. So if we run this on the device, we can assume that this number is going to be doubled. So we're something like 2,000 draw calls for this scene, which is just not within the realm of sanity for this device. We want to be closer to 100 draw calls a scene, or 150 maybe. I'm going to take a step back and say, like, how many people know what a draw call is? All right, that's pretty good. Cool. All right. If you want to know like more about the nitty-gritty of like how the mobile render pipe works, there's a video of me giving like a version of this talk from Oculus Connect 2 like 2 years ago. And I stole this slide out of it, so I wouldn't have to make a new slide. But you could go back and watch that, and it's got a lot more detail. But at a high level, a draw call is a command to draw a mesh that you submit to the sort of the mobile GPU driver. And the cost is incurred on the driver's side, and it's fairly expensive. And what it is essentially you say, well, I'm going to render a mesh, and that mesh has a bunch of state. Like it has a texture, maybe it has a shader, and it has a location in the world. And generally, the way that you would render those things in OpenGLES is you would say, I'm going to set my shader, I'm going to set my texture, here's the position, now draw the mesh. And that collection of setting the state and drawing the vertices is what we think about when we say a draw call. And the expensive part of that is actually not the submission of the verts. It's actually the work that happens to bind the shader to the vertex stream that you've submitted. So your vertex stream says, well, I might have texture coordinates, and I might have color, and I might have other stuff, and the vertex stream has some random stuff in it, and the shader has to match those things up. So what we're going to try to do in order to reduce the total number of draw calls is we basically want to change state less often. We're going to take as much of the scene as we can and bundle it up into one really large mesh. Unity calls this a static batch. And then we're going to try to say, like, OK, I want to set my shader, I want to set my texture, and then I want to render as many things as I possibly can. And if we can do that without changing shader and texture and those sort of what Unity calls a material, then we can get significantly more efficient rendering because the cost of each individual draw call will go way down. So our goal is to statically batch most of this scene. We can tell right now that we are totally failing at that goal, although it's offset here. The total, the total number of draw calls that were saved by Unity's automatic batching system is 0 right now. So we are getting no efficiency out of Unity's sort of built-in systems. We can also see that we have a lot of passes. A pass in Unity parlance usually means that the shader has changed. And it could be because you have a shader that has multiple passes within it. Perhaps it's real-time lit, or it's got specular, it's got some other reason to render the geometry more than once. Or it could be, in this case, it's probably because we're just drawing things too many times. So we want to make all these numbers better. We want to make the total number of draw calls go down, we want to make the total number of material binds go down, and we want to make the amount of draw calls we save by batching go up. The scene, I mean, there's not a lot to it. There's not much more than you could see in that initial screenshot I showed you. There's a couple of little hallways that bend off from the sides, and excuse me, there's a little area behind the wall that you can see, but it's not like there's a big building here. It's not like there's a lot of geometry things being rendered that you can't see. Also, we've set this project up properly as a, in terms of like the settings you need for a normal, efficient Unity sort of mobile scene. Like our static batching and dynamic batching are turned on, which is important. I didn't show it here, but we also have graphics jobs turned off. That can negatively affect dynamic batching recent versions of Unity. We've set up our quality settings properly. We have essentially no shadows. We have one light, although in this scene we're not even using the one light that we have. It's all baked lighting. We're using anisotropy filtering and 4x full screen anti-aliasing because those things are what you want for every Unity project, but those aren't going to affect draw calls anyway. Finally, we're using a pretty standard shader. We're using Unity's built-in mobile diffuse shader. This is a shader that only supports one directional light. It's really easy to batch. It's not very complicated. So from a sort of high-level setup point of view, this scene should be really simple. So probably something's wrong. We should be getting more efficiency than we're getting out of this. What I'm going to do is I'm going to go use the frame debugger. How many people know about the frame debugger? Oh, it's pretty good. So frame debugger is a pretty new tool. It showed up in Unity 5. Damn it. Oh, they should not give me this button. What it does is, did it come back? No, which button? That one? All right. What it does is it allows you to step through each of the draw calls that are used to draw your scene. And you can see kind of how your scene is put together. It's a super useful tool. Even if you aren't trying to do draw call optimizations, I highly recommend that you open your scene up and sort of walk through it with this thing, because it gives you a sense about how Unity puts your scene together. And we can open it up here and we can see, draw mesh, draw mesh, draw mesh, draw mesh. Each of those is one of our draw calls, and we got a ton of them. Actually, if we look at it, yeah, here we go. Lots of draw calls. The other thing that's important here is that we can see the parameters to each draw call. And that's gonna matter later because we're gonna want to have those parameters be basically the same in order to generate a large static batch. Don't need to care about it right now. When we look at this, one of the things we can see is that we're kind of drawing everything more than once. Like I noticed we're drawing the sine 4 times, we're drawing the vent pipe twice. There's a lot of duplication in this list, which suggests that maybe we're not batching anything because these objects aren't actually set up correctly. So I went in and I looked at the pool table, just one object in the scene here. And lo and behold, it has more than one material assigned to it. So the problem with multiple materials is, in order to render an object with multiple materials, you render it once and then you change the material and you render it again. And because you had to change the material in there, that prevents Unity from putting it into a larger static batch. So it's fairly common in my line of work to get a project from a developer that they're having trouble make fast and sort of look at the art assets and find a mesh that has 4 or 5 different materials on it. And the way that this happens is that it's easy for an artist in Maya, for example, to assign several textures to a single mesh. And when that gets exported and re-imported into Unity, it comes out as a mesh with multiple materials, which then gets drawn multiple times and also cannot be batched. In this particular case, it's actually just a mistake. This thing should only have one material. It's only intended to have one material. And I can easily remedy it by just removing one of the materials. Usually it's not that easy. Usually you'll have to redo the art or maybe there are some tools on the Unity Asset Store like MeshBaker, which can help you break a mesh apart so it's just one material per mesh. But we want to do this because if we have multiple materials, that object by definition cannot be well batched. So if we do this to the whole scene and we remove all of our material duplication, we go back to the frame debugger and see that we've made a lot of improvement. Now we don't have all that duplication in there. But we still have a huge number of draw calls and they're still not getting batched. The frame debugger will give us a little hint about why that might be. And in this case, if we zoom in on it a little bit, it's like, oh, well, we're not batching because your objects have different materials. I guess if we think that through, it kind of makes sense, right? Like our goal is to set our shader, set our textures once, and then draw as much as we possibly can. So if we're going to change the material from every object, then by definition, we can't put those objects together. And in fact, the reason that might happen is a fairly common reason is that we have a separate texture for each object. We got a texture for the chair, we got a texture for the wall, we got a different texture for the pool table. And if we do that, then that's going to require each of those be a unique material, and that's going to cause all those things to fail to batch. So the next step here is to go make some Atlas textures. Atlas textures are just big textures that have all of the textures in a single image, and then they are UV'd. The mesh is UV'd into this image by the artist, or again, by a tool like MeshBaker, in order to unify the material across all of the scene. So once we do that, I can go back and now I can say, I'll select all the pool balls in the scene. And you can see on the left side that the pool balls are all selected, but on the right side, you can see they're all using the same texture, the same material. And that's because they're now part of a larger atlas. One thing to be careful of when working on materials, and particular material instancing, is that in order to batch, Unity requires the material pointers be the same. It actually doesn't care if you have 2 of the same material, but they're actually one's a copy of the other. In that case, those things will be considered different and won't be batched together. And it's really easy to accidentally create a copy by accessing the material property that's on the renderer class. If you write code like this, where you just say, oh, my renderer.material does something, immediately that code implicitly creates a copy. And you can tell that's happened because the word instance is added to the name of the material in the renderer. If you do this, even though your material is originally the same as everything else, this thing is now opted out of batching. And so you want to be careful not to do that. OK, so what did we do? We fixed the duplicate material issue. We went back and we remade all the art to use a single Atlas texture, as few materials as possible. And we can go back to the statistics thing and just see what the result of that is. And you can tell, already we've dropped our draw calls in half. Actually, we can even do better than that, because what we're looking at here is the total number of draw calls required to draw the scene without static batching. And that's because we haven't hit play in the editor yet. The moment we hit play, what Unity is going to do is it's going to take all of the objects in the world that we've marked as batching static. That's a little checkbox kind of on the side of the inspector. Everything we've marked as batching static, and it's going to generate that large mesh. And it's going to say, OK, how many of these things can I actually make into a static batch? So if we hit play, we'll see the effects of that, which are that all of a sudden we're getting some like 300 of these objects are now being put into a single batch, and we're able to draw them much more efficiently. So we're still at 173 batches, which is too much. We want to get these draw calls down to like 50 or less. But we're making progress, right? We can go into the, as the application is running in the editor, we can go into the frame debugger and actually see the static batches that Unity has generated here. And now instead, before it was draw mesh, draw mesh, draw mesh, draw mesh, and now we have static batch, static batch, static batch. Furthermore, if you're interested in this stuff, you can go into the renderer and you can find the mesh that got generated by Unity, and you can sort of zoom in on it and see what it looks like. And this is just some random one that it put together. Who knows what heuristic it uses to sort of collect objects, but anything that's marked as static and is using the same material is a candidate to be put into this larger mesh. Now would also be a pretty good time to mention that we have some other tools that we ship with our sort of package of tools. There's a package you can download from a website called Oculus Utilities for Unity 5. And if you're not using it, you're doing it wrong, because you definitely want to use it. It gives you a whole bunch more control than the sort of standard VR Unity interfaces give you. And also includes a couple of tools like this one. This is a tool called OVR Lint. It shows up in the tools menu under Oculus. It says Audit Project for VR Performance Issues. And what this does is it runs over your scene, and it makes a bunch of recommendations for things that you could improve. So I ran it on this scene, and there's actually quite a lot of stuff, and I didn't want to scroll down. But you can see the top of it. It says, well, I got some extra camera clears in there, and I have a bunch of materials that look like they're multiple paths, which I want to avoid for batching reasons. So these are suggestions of things you could fix. There's actually quite a bit more if I scroll down. The caveat to this tool is that you don't want to blindly apply all these things. Some of the suggestions are destructive. The tool can't tell what your intent was. It can only look for sort of patterns. So if you just went through and did everything that the tool said you should do, you might break your scene. But it's a pretty good way to find areas that you might be able to easily improve. Turns out when I ran this, it didn't have too much to tell me. I know where the problem is. The problem is draw calls. But it's cool. It's still a pretty good tool to use. So now that we're down to what was like 170-something draw calls, we should run it on the device again and see what we're doing. So we're getting there. We're getting better. We've gone from 30-something frames a second up to about 45. That's pretty significant progress, but it's not shippable yet. So what's the next step? How are we going to further improve this? Well, if we go back and look at the frame debugger again, one of the things the next hint that it's going to give us to say objects are light mapped, which is kind of a weird thing for it to say. It's kind of a cryptic message, because light mapping, shouldn't break batching by itself. A light map is essentially just another texture. It's kind of a secret input to your material. It's another texture that gets rendered on top of the mesh that you're rendering. And as long as that thing conforms to all the other rules that we already said, we should be able to set a light map and render a bunch of stuff. So I guess we should dig in on this. If we look in at our light map settings, they aren't particularly complicated. This scene has no skybox because you can't see the sky. I'm using I'm not using real-time GI because it's not appropriate for mobile. I'm using baked lighting. I'm using Unity's new progressive lighting system because it's pretty cool. Nothing here is particularly out of whack. It's worth noting that I'm using non-directional light maps, which means that I have a single texture for each light map. A directional light map generates two, but I don't need those because I'm not doing real-time lighting. So far, so good. We could go look at the light maps themselves. They're not particularly complicated either. They're just textures that Unity calculates and puts over the scene. What we can tell by looking at this scene, though, is actually we have kind of a lot of light maps. And if we consider light maps to be like a secret argument, like another secret texture that's inside your material that Unity doesn't show you, but it still has to bind, then you can see how, if you have different light maps for different objects, that's actually going to break Unity's ability to batch them. Because normally we'd be like set light map, set material, draw everything. But if we might be set material, set light map, draw, set light map, draw, set light map, draw, and that would be baking batching, right? So I guess the next question is, why don't we have so many? If you scroll down to the bottom, it turns out we have like 42 of these guys, which is like a ton. And the reason is that some jerk, which is me, set the maximum size to be 256 by 256. And that is a mistake. I don't want a lot of small light maps. I want one really big light map. So we can change that pretty easily. It's a setting in the light map panel that we just looked at. I'm going to pump it all the way up to 4096 by 4096, because my goal here is not to save memory. It's to improve my draw calls. Light mapping takes a while. You sort of wait for a little while, and then it'll render. And then you're going to get a texture that looks like this, right? This is the 4096 that got generated from light mapping this scene. And like, there's a part of me, sort of right around this chest area right here, it's my old programmer part, that looks at this and it's like, look at all those empty pixels, like, how much freaking memory are you wasting with this? But the newer part of me says, I don't care, because actually I'm not memory bound on this device. I've got quite a bit of memory to spare. And if I can take 256 or by 256 textures and pack them all into a single 4096 and get my draw calls down, that's actually a really significant improvement. And I don't mind if there's a little bit of waste. Well, let's see, like, how much improvement is it actually? Go back to our statistics pane and look. It's pretty big, right? We just dropped like another 100-something draw calls off of the scene. You know, we can see that we're now batching significantly more efficiently. We're now, total number of draw calls is smaller. And we're being pretty efficient with the way that we use our passes as well. It's also sort of important to note that the scene hasn't changed visually, right? We've done all this stuff to it, but it looks the same as it did at the beginning. So we haven't actually degraded the quality of the scene or changed it in any way. All we're doing is organizing the data in a way that'll be more efficient for the GPU to execute. And we can also see that we've gotten rid of like even more of the batches. Now we're just down to static batch, static batch, static batch, static batch. That looks pretty good. Up until this point of the talk, I think that we've been talking about things that are basically the straightforward way of making Unity batch scenes more efficiently. Probably the folks that raised their hand when I asked how many people have shipped for Gear VR, you've probably all done all this stuff already. And you know this and you're like, why did I come to this talk? I made a mistake. So next I want to talk about unorthodox methods. And they made me make the interstitial for this, even though I didn't want to, because the point of this part of the talk is that these are ideas or things that you could do. Maybe they're not appropriate for every project. In fact, some of them for sure are not appropriate for every project. So I want to caveat them with just, I want to throw these out there as ways to further reduce draw calls that are a little bit more lunatic fringe. Maybe they're good, maybe they're not, but maybe they'll give you an idea for how you could optimize your own scene. Probably shouldn't just apply these without thinking about them. OK, so caveats aside, let's go back. This is a slide from earlier in the talk where we were talking about how the frame debugger works, and we were looking at all the crazy draw calls we have. But I actually want to not look at the draw calls for a minute. I want to look at the scene. If you take the frame debugger and you sort of hit the arrow keys and walk down the content of the scene, you will see the objects draw in. And what you'll notice if you look really closely is generally the opaque objects are going to render from front to back, and the transparent objects are going to render from back to forward. And that is a really reasonable way to render geometry in any game engine. The reason you would do that is that you know, in addition to draw calls, another thing that these types of devices get bound by is pixel fill. Right? We want to fill as few pixels as possible. And so it's also important to optimize for overdraw. Ideally, if I'm going to draw this scene here, I don't want to draw all this stuff and then draw something that's actually right in front of it, because I've wasted a bunch of pixel fill. And you know, if you're drawing sort of front to back, then you can use the Z-buffer to sort of opt out of pixels that you don't need to draw, and then therefore you can save on fill, and it's a really standard, normal way to draw an opaque scene. But right now, I don't care about pixel fill. Pixel fill might be a problem that I have in the future, but right now it's not my problem. Right now, my problem is draw calls, and I want to make draw calls faster. So I would like to change the order that objects draw in order to make them batch more efficiently. If you think about how this probably works, like I've never seen the Unity source code, and this is all my guess. But if I were Unity, the way that I would organize the algorithm for drawing the scene is I'd take every object that's in the scene, and then I'd cull it by the frustum. So I have some list of objects I can see in the frustum. And then I'd sort it from front to back, and that would be a list of things that I'm going to draw. And that's basically what we see in the frame debugger here. And then to batch, I'd probably say like, OK, first object and second object, can you batch together? Yes. OK, great, you're a batch. Third object, can you batch in there? Sure, you're a batch. Fourth object, can you? No? OK. Now we've got one batch, we're going to draw that. Let's go on to the next one. And they would just sort of create buckets in a linear fashion as it went down from the top. I'm pretty sure that's how it works. If that's how it works, then maybe we can change the order of our draw calls in order to put objects together that we know are more likely to be bucketed together into a batch. And because what we know that the thing that causes batching to be more efficient is a single material, what we could do is just sort of organize everything by material instead of by front to back. The code to do that looks something like this. It's actually not very complicated. You could make it more complicated if you want to. The important part is that last line there that sets the sorting order. All this code is doing is walking through a bunch of different objects, picking out the instance ID of the material, which is just a unique identifier, and slamming that into the sorting order. And all that's going to do is say everything that has the same material is going to have the same sorting order, and it's going to force all those things to get bucketed together. So that sounds like a cool theory. Let's try it out. So if we go ahead and do that and then run it on the scene, we'll see what the effect is. Not bad, right? Down from 50-something to 20 draw calls. And we're better batching and almost 50%, set pass efficiency there, which is pretty good. I have to now caveat this particular approach because you might be saying, like, why would I just not do this for everything? What we've done here is great for this scene. It makes it much more efficient. We're telling Unity, we're giving Unity more information than it has about the scene in order for it to use its existing systems to render it more efficiently, and I think that's always good. However, we've also broken some of the rules. For example, I've also applied this with that code I showed you a minute ago, not only to opaque objects, but also to transparent objects. And transparent objects render the opposite of opaque, right? They render from back to front. And the reason that they do that is if you have, say, a window pane, and behind the window there's a glass, and behind the glass there's a poster, I need the poster to be tinted by both the glass and the window pane. So we draw the poster first, and then we draw the glass, and then we draw the window on top of it. And that's a back to front rendering, and that's how we ensure that the blending for transparency is accurate. But I've just thrown the order for all transparent objects out the window because I decided I wanted them to be sorted by some sort of material thing. So if I have overlapping transparency in this scene, it's probably not going to look right. Or it might look right, it might not. I've lost control. Fortunately, I don't really have that case. This particular scene is quite opaque. A more reasonable implementation of this algorithm might be to only apply it to opaque geometry, or only apply it to scenes or areas where you know that it can be, you can break that rule. Something to think about. In fact, if we can look here at the frame debugger and see, I got a big win out of making the transparent draw calls batch together. Now they're super duper efficient, but they're totally not rendering in the right order. For me, that's okay. Might not be okay for you. So let's see what the effect is. Yay! We made it to 60. So this is cool, right? Because what you're actually seeing here is the screenshot behind here is the original screen. I mean, it looks the same as it did when we started, but we started with 900 something draw calls, and we're down to 20 per eye, and we're hitting 60 frames a second. We're hitting it pretty consistently as well. This would be a great place to stop and say, I'm done. And for this particular project, that's probably what I would do. But other projects are more complicated and can't stop here and have to do more. So let's keep going. We'll talk about how light mapping can affect our draw call efficiency. I talked about light mapping earlier as being just essentially a second shade or a second texture. It's a secret argument to your shader that gets drawn, gets blended with your regular shader. With your regular texture as it's drawn. Nothing about that should intrinsically break lighting. But if you think the implementation all the way through, geometry has a UV channel that usually goes from 0 to 1 that maps the texture of a vertex into a texture map. And in Unity, it's very common for us to have a UV2 channel, which is a second set of UVs, which usually also go from 0 to 1, which need to map into the light map texture. And the problem is we just created one giant 4096 by 4096 light map texture. So when I select the outside of this object, I don't want it to be mapped to the entire light map texture. I want it to be mapped to some tiny little subset that happens to describe the shadows for that object. And you can see it here. I've got the outside of the room selected, and it's highlighted in blue, the little section of the light map that maps to. But when Unity renders light mapping, it doesn't touch your UVs. It doesn't go in and change the mesh in order to point it into the light map. Instead, what it does is it creates a field, which is a scale and an offset. That says, I know you've got these UVs that go from 0 to 1 or whatever, but I need to shift that over and scale it way down in order for you to map into the little section of the light map that I want you to use. And that's called Unity Light Map ST, scale, transform, scale, offset. API is not consistent on the naming. This is usually not something that you have to care about, because if you have static geometry that gets compiled into that big mesh that we talked about before, then Unity is going to take this Unity Lightmap ST and it's going to burn it into the UV channel, which means that this field is going to go away. By the time you get to the static version of the mesh that you have, it's already going to be burned in there, and the UVs will map directly into the light map, and everything will be fine and dandy. The edge case where that doesn't happen is where you have a light mapped object that's not static. And it's kind of an edge case because usually light mapping and static sort of go hand in hand. But it's actually a more common case than you would think. It's very common, like in a Gear VR game, for example, to have like a doorknob that you want to turn. And the doorknob has like lighting on it that came from light maps, but you still want to be able to turn that doorknob. If it's static, you can't animate it. You can't even do the turn. And when it turns, you know, like the shadow on it is not going to be correct, but nobody's going to care because you're going to see it for 2 seconds as the door opens. So it's actually fairly common to end up with objects that aren't marked as static, but are still light mapped. And those things are not going to batch because this Unity Lightmap ST field in here is going to prevent it, because each one of those has a unique scale and offset. So we can fix that. We can use code that looks like this at runtime to walk through all of the UV2s of all of our meshes that fit that profile and just do the same work that Unity does when it makes a static batch, just sort of burn in the Lightmap ST into the UVs. We can't do this at editor time yet. It'd be nice to do this offline before we even sort of run the application. We can't because you don't actually have access to Unity Lightmap ST at editor time. You only have access to it at runtime, and that's because at the moment it's kind of locked up inside this opaque object called lighting data. Unity tells me that they plan to build an API to allow you to do this stuff in the editor sometime soon, but for the moment you have to run code like this, at runtime, maybe like when your scene loads. If your use case fits this use case, like you have objects that are light mapped but are not static, then this can be a way to dramatically increase the sort of batchability of these small objects that can't be static. Another thing we didn't talk about very much here because it didn't fit this scene is occlusion culling. And occlusion culling is a system by which if I have say in this sort of bar that I've set up, there's really only a single room. But if we imagine that there are more rooms behind it and they all fell within the frustum of my camera view, there's no way to know that those objects that are behind a wall in another room don't need to be drawn. By default, without any occlusion culling, I would draw them all. I would say, I'd draw the objects in the back, and I would end up drawing a wall on top of them, and you wouldn't see any of them, and I'd waste a bunch of draw calls on it. So occlusion culling is a system by which you can say, from this point in space, here's what I can see, and then limit the total number of objects that you draw just to that. And Unity has a system for this built in. Unity's system is based on a very battle-tested technology called Umbra. And when it works really well. You can just sort of turn it on and run your scene, and sort of you bake some occlusion data, and it runs, and then it turns off all the meshes for the things you can't see, and it sort of does it automatically as the camera moves. Sometimes it's difficult to control, though. I found, particularly for indoor scenes, it can be pretty hard to make it do what you want. If it works great, and if it fails, it's sort of hard to debug. And the debug tools that come with it can also be kind of mysterious. Like these green lines are ostensibly visibility lines, but they pass through walls. Kind of hard to tell what that means. If you're really serious about doing better occlusion culling, and you had a system that was a bunch, for example, like a building that had a bunch of packed tight rooms, where it was important to actually occlude the things that you can't see, you could go a step further and write your own occlusion system. Here's the one that I wrote. This is an occlusion system that takes a point in space and it renders a panorama of the scene. And it renders it with a shader that colors each individual mesh a different color. And then what you do is you sort of render this panorama with this shader, and then you walk over the resulting texture and you map the colors back to mesh instances. And what that gives you is a list of things that you can see, from this particular point in space down to the pixel, the meshes that you can see from this spot. And this is what's known as a potential visibility set, right? Because it's a 360 panorama, there's not going to be a case where you see all of these objects at once. They're still going to be frustum culled. But it gives me an idea. If I was standing right in this space and I've rendered this panorama and I've done the work to compute the things that I could potentially see are all in this list. And importantly, things that I can't see, like the stuff that's in the room behind the walls, are not in this list. The drawback to this kind of system is A, like it's kind of a lot of work to build, and B, like this just only works for a single point. Like I don't have a way, the basic version of the system does not have a way to deal with like a moving camera. But this can be extended. This can be extended to a system that has a bunch of different points sampled around the scene that you then interpolate between. What you're seeing here is a character walking through a space that has this, and the green line is the camera's forward direction. And you'll see, like, as the character opens doors, things will turn on. As she moves through the space, things are going to turn on and turn off. And this is essentially that same potential visibility set system running as the camera moves to sort of dynamically turn off objects that we know you can't see. As she kind of walks over to the living room area, you'll see the kitchen on the bottom left mostly just turn off. And it's this implementation is actually fairly simple. The algorithm for it is not something I invented. It's something that's been around for quite a while. This is a type of work you could do. I'm sure you could come up with a much better algorithm than I came up with for this. But taking control of the content of your scene and ensuring that when you're in a particular space, you can only see, you're only asking Unity to batch or draw the things that can actually be seen is a pretty powerful way to improve your overall sort of draw call performance. I also want to give just a very quick call out to this script called Ovr Overlay. Actually, how many people have used Ovr Overlay in a game project? So yeah, a couple, okay. So Ovr Overlay is the Unity interface for a technology that we have in our SDK, which is called Compositor Layers or Time Warp Layers. The idea with this technology is that we can take some geometry, something simple, and a texture, and instead of rendering it in Unity, we can have Time Warp render it for us. And the reason that we would do that is that Time Warp can generally render it at higher quality. For example, if we wanted to render like a movie playing on a quad, if we render it in Unity, it's going to get distorted once by Unity's camera, and then it's going to get distorted again for the lenses. If we have Time Warp rendered, it only gets distorted one time for the lenses, so we get less artifacting. Another reason you would use overlays, or for example, Time Warp can render the overlay at 60 frames a second regardless of the frame rate of your application. So if you take, like, if you have a headlocked reticle that's like floating out in space, if you make that reticle graphic a quad that is an overlay, it can track perfectly even if your game application is not making 60 frames a second. If you don't do that, what you'd see is your reticle would kind of judder in space like that as you move your head. There are some applications that there are just little areas where you have a little bumpiness and you can't fix it. One way to sort of cover that up is to use a Time Warp layer. I want to talk about one other way, which probably you didn't know about, which is a cube map being rendered by Time Warp. And the nice thing about the cube map is, you can have a 360 cube map environment that has perfect head tracking, even if you don't ever render another frame. So, for example, when you go into your level load, like when Unity starts to load a level on mobile, generally it stops rendering. It becomes I/O bound, and the frame rate really falls apart. And with head tracking, that's a really poor experience. But if you set a cube map to be rendered by Time Warp during that load, you can stop Unity rendering completely, and the user will still have a nice 60 frames a second head-tracked environment to be in while you load your level. You can also do this thing called an underlay, which means that the cube map will be rendered first, and then your eye buffers will be composited on top of it. And you can cut holes out of your eye buffers with alpha, and they'll be blended on top. And that means you can essentially use Time Warp as like a super badass skybox. This is a simple system. Like if all you're doing is standing at a window looking at a landscape that's outside, and that landscape is pre-rendered and it's a cube map, there's probably not a huge advantage to doing this with Time Warp versus just doing it in Unity. But if you start to think about, like, what could I get if I rendered my background for free, you could start thinking about systems where, for example, your far clip plane is much nearer than the content of your background. And as you start to bring things in, either with level of detail or with a fog, with a fade, you actually blend things out of the 2D far plane, which is actually being rendered by Time Warp, into the foreground, which is being rendered by Unity. And you could probably come up with some pretty tricky stuff to get your overall scene complexity down while making it appear to be very complicated. I wanted to call this one out because it's not well known, and I think it's underused, and it's pretty cool tech. One other thing I wanted to mention is if you saw the keynote, I was talking about multi-view. In Unity, multi-view is called single pass stereo rendering, and it makes this entire discussion a lot easier because essentially what it does is instead of drawing the entire left eye and then drawing the entire right eye and therefore sort of doubling the total number of draw calls that we need, it draws into both the left and the right eye textures with a single draw call. So we'll say draw, 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 and then we're done. It makes each individual draw call slightly more expensive, but it halves the total number of draw calls that are needed to render the scene. So in practice, this is something like, I think the maximum is like a 40% improvement in the overhead of draw calls. And since draw calls are usually the long pole for any kind of mobile VR application today, that's a pretty significant thing. I think practically, you're more likely to see something like 20-30% improvement, but still, it's a checkbox. It's an option in Unity settings that is available in Unity 5.6 or newer, and you should absolutely use it. One last point, and I'm actually blow through the last part of here so I can leave some time for questions. But the reason that we care about draw call optimization is not just to hit 60 frames a second. That's like our initial reason, because if we're not hitting 60, we shouldn't ship. We'll make people sick. But once we hit 60 frames a second, there's still a high value in not stopping there. We should actually continue to make it as fast as possible, even if we have to use one of these sort of lunatic fringe or unorthodox methods. And the reason that we want to do that is that these devices are, they're bound not only by the performance of their CPU and GPU, but they're bound by the total overall heat of the device. And if we can take load off of the CPU, we can actually save heat, and then we can spend that heat on like the GPU. So our API has a seesaw for throttling the CPU and the GPU. This is the accessors for it in Unity. It's a value between 0 and 3. And the idea is like if you need CPU time, you crank the CPU value up and the GPU down. And if you're GPU bound, which very rarely happens, then you set it the other way. And most of the people that I work with have always set the CPU up really high and the GPU down low because they have to spend this really expensive draw call overhead tax. If we can do what we did in this talk today, if you can get this down to like 20 draw calls and turn on multi-view, all of a sudden you're probably no longer CPU bound. In fact, you might be able to throttle your CPU way down. If you can do that, that means you have heat to spare, and you can spend that on the GPU. And that means you could do things like increasing the target eye buffer resolution. Increasing the target eye buffer resolution is expensive on the GPU because it costs a lot of pixel fill. Pixel fill is also slow. Right now, it's not our long pole, but once you start doing this, normally it's a 1024 by 1024 eye buffer. If you want to go to like 1200 or 1300 by 1300 or even higher than that, pretty quickly, fill starts to become an issue. But if you've got the time, if your scene is efficient enough and you have the heat to spare because you've made the CPU faster, you can absolutely dramatically increase the visual quality of your scene by increasing the resolution of your eye buffers. It's like a one-line code change, and if you have the performance to spare, it looks fantastic. If you're wondering why Oculus Home, when you put on the headset, why it looks so sharp, that's because it's running at super high resolution eye buffers. So that is the talk. At the end of the day, we started with the scene and we end up with the same scene. It looks the same, but it's significantly more efficient. We went from 900 draw calls down to about 20 per eye, and then with multi-view, it's probably going to be 20 for the entire frame. That's a really significant improvement, and nothing here was rocket science. I hope that there's some stuff here that you can use in your own projects, and at the very least, I hope some of the other like weirdo methods that we talked about are useful for you to think about how to optimize your own scene in ways that are specific to your content. I'm going to stop talking at this point and take your questions, but thank you very much for coming.